Let me briefly review what we were talking about last time. We decided to study these homogeneous isotropic universes. The universes we studied would have metrics of the form minus d tau square plus a squared of tau eta I gamma ij dxi dxj, where this gamma ij was some sort of spatial isotropic homogeneous space, and we discussed that there were three possibilities for this space. The simplest was just flat space, which I'm not going to write down. And there was the sphere, the S3, which was d chi squared plus sine squared chi into d theta squared plus sine squared theta d phi squared. This was unit S3. And then there was a unit hyperbolic space, okay, which was the same metric, but the sign became sin h. Oops, yeah. Let's call this H3 unit. Okay, so this was a metric. Our Einstein equations, please help me with the factors and the positioning of lambda, but let me write it out. R mu nu minus R g mu nu by 2 is equal to, what is it, 2 lambda? Sorry, lambda g mu nu minus lambda g mu nu minus lambda g mu nu plus 8 pi k by c cube g mu nu. Was that right? What? Okay, 8 pi g by 4 c to the power 4. Let me k is g. Thank you so much. Okay, so this was our Einstein equation, and we wanted to write down this equation. We discussed the systematics of this equation last time. We discussed that that this Einstein equation here could have either two zero indices, two t indices, or two spatial indices. There's only one equation where it had two spatial indices, because all the equation where it was completely two spatial indices was proportional to the metric of space. That was from homogeneity and so on. And we discussed that there was a consistency relation, that if this stress tensor was conserved, okay, then there was a consistency relationship between these two equations. Okay? Another way of saying it was that we could take any one of these equations and the Bianchi identity for these equations as our two independent equations, because we know that they are all consistent. That was the philosophy we decided to adopt. Now, had we had something of being its own equation of motion here, the stress tensor would automatically be conserved, as we discussed sometime in our course. However, we're going to take not a fundamental but a phenomenological approach for the study of the rest of the universe other than gravity. So we don't have our fundamental equation for the stuff that's going on. We're not going to write down Maxwell equations for the photons, for instance. That's too difficult. Okay. Also, we're not terribly sure what most of the universe consists of. We don't really know the fundamental rules. So we're going to be pragmatic. We take a phenomenological approach. Okay. And so what we're going to do is postulate certain properties about the stress tensor, and the equation of motion of these properties plus the equation of motion will be, plus the conservation of the stress tensor, will be effectively the equation of motion for this remaining stuff. So before we proceed on this, I just want to give you 2 minutes on that general philosophy. Okay, as a general statement. just so you understand the logical structure of what we're doing. Okay, consider in a fixed background space-time. Okay, suppose I have a substance such that T mu nu, its T mu nu is given by epsilon u mu u nu. I'll tell you what all this means in a moment. Okay, epsilon u mu u nu plus p into g mu nu plus u mu u nu. Okay, so what's the idea? What we're doing here is hydrodynamics, like what we're going to be doing for cosmology. We've got some stuff, we don't really know that much about it. It's like the air in this room, or a gas of photons for the cosmic microwave background. We don't know too much about it. We're going to parameterize this stuff by its energy density and its pressure, but that's often not enough. Actually, in this cosmology case, it will be enough because of the high symmetry of the problem. But in a general case, we also need to parameterize it by how fast the stuff is moving. Now, we're not parameterizing it by how fast each photon is moving, how fast each atom is moving, how fast the conglomerate of stuff is moving. Okay? So we've got an idea, we've got in mind some sort of coarse graining. Imagine we go to length scales that are large enough so any little box on this length scale contains many particles, but small enough so that within this length scale, the substance can be thought of as thermally equilibrated. Now, a whole medium is not thermally equilibrated, otherwise it wouldn't be moving, wouldn't be doing anything. But it's thermally equilibrated on short length scales. Imagine in this room there's a mean free path between molecules. Okay, that sets the length scale for equilibrium, of local equilibration. So imagine a lump of stuff which is large compared to the mean free path, but small compared to the length scale of variation of pressure, or variation of this macroscopic velocity of the medium. On these intermediate length scales, roughly you can use thermodynamics because things are locally equilibrated, patch by patch in each little local region. So thermodynamic notions in some approximate way make sense, lump by lump. Okay? And yet have these thermodynamic variables varying in space-time. You know, it almost sounds like an oxymoron. Thermodynamics, what happens when everything comes to equilibrium? We're not yet in equilibrium, yet we're using thermodynamics because of the separation of length scales. Okay? We've got some sort of local equilibration. Now, so in general we've just written down a stress tensor like this, but suppose we've got this notion of local equilibration. Then we know what this is. This is the locally equilibrated energy density, rest frame energy density of that stuff. Okay, by the way, this thing here is the projector orthogonal to your velocity. So this is the local notion of space. That's why wherever's behind it is pressure. Okay? So this thing here is the local notion of energy density. This thing here is the local notion of pressure. And since we've assumed that everything is locally equilibrated, if there's no other conserved quantity in the problem, the only conserved quantity is energy and momentum, then these two functions are now independent of each other. They're related by the equations of thermodynamics. Okay? Just so that you're very clear about this, let me remind you how that goes. In any system where there's only one effective local conserved quantity, namely the energy, all of thermodynamics is specified by the partition function. Okay, let's call it z of beta, which is e to the power minus beta h trace. Now suppose I gave you this z, which is a function of beta's inverse temperature, and I wanted the energy out of it. Okay, what would I do? I would take del log z by del beta, and that would be equal to minus the energy. Just because you differentiate this with respect to beta, you pull down minus h. Suppose I wanted instead the entropy of the substance. Okay, what would I do? Well, you'd say, look, if I got log z, I have e to the power s minus beta h. Because that trace is like, in a thermodynamic limit, dE e to the power s of e minus beta e. That's the idea, right? S is the effective number of states at energy. So this trace translates to this. So if I calculate log z in some saddle point way, what I've got is S minus beta E. But now I know what E is. Okay, so S is equal to log z plus del log z by del beta times beta. Right? That's what S is. Now, sometimes we are interested in this thing called the free energy. We won't need much of this, but just to get it. So make sure you understand the logical structure of what's going on. The free energy is equal to minus T log Z. Okay? And it's a wonderful fact about thermodynamics that this free energy is also minus the pressure. Okay, this I'm not going to derive for you, but I'll ask you to do yourself to check. You know this in some way. Okay, so this free energy is this, and P, which is minus the free energy, is T log Z. Okay, a relationship that's sometimes of interest is the relationship between pressure and entropy. I'm going to just differentiate this, but I'm getting a sign off. Did I get this sign right, please? That's minus. Thank you. Okay, now it makes sense. Okay, so now if I just differentiate this quantity, I get del P by del, let's say T, is equal to log Z plus T del by del T of log Z. But T by del T is minus of beta del by del beta. Okay, which is equal to S. Of course, all these relations, as you say, it's a Maxwell relationship, and all these relations were known in thermodynamics well before this way of thinking about. But I don't know about you, but I find thermodynamics very mysterious. I always think of things through, through what the definition is and then derivation.
So there's no volume in this, right? Because the Maxwell relation relates del S, del V to del.
You can now think of it, if you want, in a fixed volume. Okay, but in this case, P here is just an intensive thermodynamic quantity. It's pressure per unit volume. Okay, and this will be an entropy per unit volume. Okay, now you can try to put it in a box and think about changing volumes. That's another game. This is just, imagine that there's an overall volume of space-time outside, and that's just held fixed to everything I'm doing. I'm not changing that around. In fact, by changing that, you could derive that the free energy is related to the pressure.
Yeah, because volume has to be fixed to 1, because otherwise free energy is extensive and pressure is intense.
Exactly. So this is, I've been rough here. Exactly, volume is 1. So actually free energy is volume times pressure with a minus. With a minus sign. Okay, sorry, so this is an overall volume somewhere. Okay, now there are two things I want you to take away from what we just did here. Okay, the first thing you want to take away is this. The first and most important thing is this. There is one function of temperature. If you know which, you know everything. If you know z of t or z of beta, you know the energy as a function of temperature, you know the entropy as a function of temperature, you know the pressure as a function of temperature. Since everything's in terms of one function of something, you can trade it for one function of something else. Okay? And a lot of thermodynamics is that. If instead of thinking of things as a function of temperature, suppose you thought of things as a function of energy. Or suppose you thought of things as a function of God knows what. Okay? You can keep playing that game. But the important thing is that there's one function. Okay? So the epsilon, the first important thing to note is that the epsilon here and the p here are not independent things. There's one function, you can think of them both as a function of temperature, or you can think of pressure as a function of energy or whatever. You know, there's one independent function rather than two because of local thermodynamics. Is this clear? Now, this makes conservation of the stress tensor a closed dynamical equation. Why is this the case?
Could you please repeat that?
This fact makes conservation of the stress tensor a closed dynamical equation for the stuff propagating around. Why is this the case? Well, in d dimensions, how many equations do we have from conservation of the stress tensor? We have d, because they're d-free indices. How many variables do we have? Well, one, because p and e are not independent. I know p, I know. But we also have u mu. U mu is the velocity. The velocity has how many independent components? D minus 1, because u squared is minus 1. So d minus 1 plus 1 is d. So you have d equations and d variables. So if you put in this form of the stress tensor, together with the local equations of thermodynamics, you now have conservation of the stress tensor giving you a closed dynamical system. So it becomes a consistent equation of motion for velocities and temperature, local temperature for instance, that you can solve. Okay? So this is the structure from a fundamental point of view of the equations of thermodynamics. It's an assertion of what form the stress tensor takes in terms of local thermodynamical quantities. And the interesting thing is that when you make any such assertion, you're going to get as many equations as variables. And then conservation of the stress tensor gives you a set of equations of motion which you can then try to solve. And that's hydrodynamics. Those are the equations of hydrodynamics. Okay? So this is the general philosophy we're adopting in the program of cosmology. It's a much broader philosophy. You can adopt it not necessarily in general relativity. You see, everything we said is independent of whether everything we said was for a fixed background metric. Okay? Now, in general relativity, Einstein's equations imply the stress tensor has to be conserved. If you derive the stress tensor from Lagrangian, we saw on general grounds it would always be conserved. If you just postulated a phenomenological stress tensor like we do, the Einstein equations would be inconsistent unless the stress tensor was conserved. Because the left-hand side is conserved by the Bianchi identity. Therefore, the right-hand side must be conserved. By the way, G mu nu is always conserved. So everything is conservation of this matter stress tensor. Okay? So if you postulate a form like this, it's inconsistent to even postulate such a form without postulating that it's conserved. Okay, within Einstein's equations. And that, coupled with local thermodynamics, now gives you effectively as good dynamical control as if you knew you were actually working with the right-hand side whose equations of motion you knew at a fundamental level. And the key point is that the conservation of stress tensor plus local thermodynamics gives you closed equations of motion. Is this clear? For this reason, Einstein's equations plus hydrodynamics is a very nice natural system. Okay? Because if you put a stress tensor on the right hand side and just assert an equation of state, then you always, more generally than in cosmology, get a closed system of equations of motion. Okay? It's quite nice because all that is needed, I'll just say it again, hydrodynamics is the conservation of the stress tensor plus local thermodynamics. But conservation of the stress tensor is forced on you in general relativity. Now, in most field theories, the equation of motion implies the conservation of the stress tensor, but it's not implied by it. Okay? So if you were dealing with a more general system of dynamics than hydrodynamics, you would need to solve the equations of motion of the additional degrees of freedom. Because you need to get all the dynamical equations of the additional degrees of freedom, not just the conservation of the stress tensor. But there is one system in the world where the conservation of the stress tensor is the full dynamical content of the theory. That's hydrodynamics. So in the case that you couple Einstein's equations to hydrodynamics, or only Einstein's equations give you the full evolution of the whole system. This would not be true if you coupled Einstein's equations to Maxwell's equations. This would not be true if you looked at Einstein's equations to anything else. It would not be true for Einstein's equations for anything else fundamental. But for this phenomenological system of equations, namely hydrodynamics, Einstein's equations govern the dynamics both of the metric as well as of the stuff making up the metric. Okay? I want you to get that logical structure very clear in your head, why it's happening. Is this clear?
So what do you mean by fundamental?
By fundamental, I mean something coming from a Lagrangian whose degrees of freedom you can specify. Okay? Get it out of an action, for instance.
Can there be no effective Lagrangian description of hydrodynamics?
Okay, it's a very good question. At the level of perfect fluid hydrodynamics, there are, though they're contorted descriptions. However, once you correct this to add in effects of viscosity, you know how viscosity is put into this description? Let's put it by adding to this a shear tensor, where this is derivatives of the. Once you do that, hydrodynamics displays behavior that no phase space system does. Namely, you have initial conditions, you have bunches of initial conditions, all of which give you the same final condition after a long time. You know, there's a thing in classical dynamics called Liouville's theorem, which tells you the volume of phase space is conserved under arbitrary Hamiltonian evolution. It never happens that in a suitable way of thinking of it, once you have the right idea of the measure, that the amount of phase space, suppose you have some uncertainty of initial conditions, that decreases in time. That never happens. But in hydrodynamics it does. That tells you that if you have something like an action description of hydrodynamics, it has to be very unusual. This is because it's dissipative. Okay? Okay. I'm tempted. I don't know. In a relativity course, are we allowed to do that? Let's do it anyway. Yeah. Exercise. Can you find for the equation of motion? Try to find an action A where the only degrees of freedom B where you allow yourself to have additional and additional. You show that it basically, okay. You'll find that in A it's not possible. If you have a second additional degree of freedom, you always can find such an action. Why? Because you take the equation of motion and multiply it by y and call that the action. This you can do. Then the equation of motion with respect to y will be your equation of motion. However, additional d of y, but making y times EOM. Okay? Choose action to be y times EOM. And then the exercise is find the equation of motion for y. And explain to me why the system is not really dissipative. This is really an aside. It's going to play very little into our main discussion. Have you understood the problem? I wanted to claim that dissipative systems couldn't easily come from actions. I just now given, if you try to find this kind of equation of motion, this is clearly dissipative. It's frictional harmonic oscillator. Okay. If you try to find an action where the only degree of freedom is x, I'm claiming you try to fool around, you'll find you can't. Okay.
So do we have to prove that we cannot?
Just convince yourself you can't. Okay. So what about try? Okay, I'll make this more specific. Try this. Tell me what's wrong with the action. It looks like x dot squared plus x dot plus omega squared x squared, maybe with a minus, maybe this with a minus. It looks like this would give the right answer, would give this equation of motion. Explain to me why it doesn't. Maybe part A is check that this does not give the right equation. Why doesn't this give the right equation? Looks like if you differentiate with respect to x. Plus minus. That looks like. Okay, that's part A. Part B is if you put a y, you can get this equation of motion. But then find the equation of motion with respect to y and explain to me why your attempt to create a really truly dissipative system fails. Slightly vague problem, just fool around, you'll see what it means. Okay. Let's go back to that. In my lectures now, we're not going to talk about dissipation, we're not going to. No, right, everything's going to be very simple. Okay. There's one more thing about hydrodynamics I wanted to say in the absence of dissipation. And that is this, that the conservation of the stress tensor as equation of motion, I've explained to you by counting, but I want to show you that there is one component of that conservation that has a very simple physical interpretation. So I want to work that out. Okay, I'm clearing this part. Is this okay? Maybe everything except dp by dt is equal to s. Well, we'll remember that. I'm clearing this part. Okay, what I wanted, the general equation of motion is del mu t mu nu is equal to 0. This equation of motion has a free index nu. Suppose I take u nu times this equation of motion. That's also an equation of motion. It's a scalar equation of motion, and I want to see what I get. Okay, I want to see what I get. So what I'm going to do is now write, well, T mu nu was equal to E plus P into U mu u nu plus P into G mu nu. Just rearranging. Now, when I take this derivative, good. So I can take it on many places. First, let's do it here. On this term, the only place where this derivative can act is P. So one term is u dot del of P. Is this clear? Because it becomes u dot del because it's contracted with a G. Now, when I take the derivative here, when I take this on this, there are three places where it could act. First thing to notice is if it acts on u nu, then we get 0. Because we will have u nu dotted with the derivative of u nu. A derivative is a small change. And because u squared is equal to minus 1, that is 0. Because u nu dotted with derivative of any derivative of u nu is half of derivative of u nu squared. But it's half of derivative of minus 1, but that's 0. Okay? So this thing cannot hit the u nu. So what we will get is u nu, but so then we'll get u nu times u nu, which is minus 1. So minus del mu of epsilon plus p times u nu. Is equal to 0. This is our equation of motion. Now, epsilon plus, I should have rubbed this part out, but epsilon of plus p is t times s. Shall I go through that again? We had z was equal to e to the power minus beta h, and this we wrote as integral dE e to the power s of e minus e by t. Okay? Now this whole thing here was p. Sorry, whole thing here times t was p. Okay? So this plus e, that cancels and you get ts. This whole thing here times t is p. So p is ts minus e. So ts minus e plus e is ts. Okay? Of course, you can always appeal to your thermodynamics, but you don't need to. You don't need to remember any of these things. And more to the point, I don't. So I need to work about it. Okay. Okay. So epsilon plus p was t times s. So this equation is u dot del p minus del mu of t s u mu is equal to 0. Okay. Now this I can write as u dot del p minus s del mu t s u dot del mu t minus t into del dot s u mu is equal to 0. All I've done is separate out this del into the part that acts on the t and the part that does not. The part that does not was here, and the part that does is here. Not done any so far. But now the great thing is that this is 0. Why is that? You see, u dot del is the small change in pressure when you move in the u direction. Okay? But you remember we had this relationship that dP by dt was s. So small change in pressure is equal to s times small change in temperature. We had dP by dt is equal to s. So dP is equal to s dt. So an infinitesimal change in pressure, see, pressure is a function of temperature. That's the point. So this dP and this dt are not independent of each other. The only way you change p is by changing t. But if you change p, you change t with an s. So this thing is dP. This d mu t s is d mu p. So these two cancel. Okay? And so this equation here is more simply, is simple. It's a conservation equation. It's the conservation equation, it's the equation of conservation of entropy. We see that in perfect fluid hydrodynamics, entropy is conserved. If you add dissipative terms, entropy is no longer conserved, it's produced. Okay? Dissipation will not be relevant for what we are going to discuss. A, because of the high degree of symmetry in our problem. And B, because, well, length scales are totally, you know.
High degree of symmetry is preventing from dissipation.
Why high degree of symmetry is preventing dissipation? Because intuitively, for dissipation to happen, this has to happen. You need the shear. But our u mu, in our case, is just along the t direction. It's not going to be doing anything funny. Okay? That's roughly what.
Spatial direction you need.
You need, exactly, you need some sort of shear. Okay? In more general configurations, you can turn on shears. Okay? And, yeah. But moreover, you know, hydrodynamics is an expansion in derivatives. And the sigma mu nu is a one derivative term compared to u mu. And we're talking about huge length scales. Okay, so these one derivative terms are quite subdominant for the discussion at hand. For other problems, you may need them.
So is it entropy current? This is an entropy current, right?
This is an entropy current. It's a local statement of conservation of entropy current. Because now, whenever you have a conserved current, you get a conserved charge,
Which is the total entropy.
which is the total entropy. Okay. Again, this is useful to keep in mind for various things. In my derivation here, I'm not going to use it exactly in this language. But Landau Lifshitz, when they derive the consequences of, maybe I'll quickly show you that. One way of thinking of it is just a statement of conservation of entropy. But okay, this is enough for my primer on hydrodynamics and its relationship to general relativity, structure of the equations of hydrodynamics. I thought I'd give this to you just because we're using hydrodynamics in our study of cosmology. And I know when I studied cosmology, the whole logical structure was not very clear. How we just put Einstein's equation, how does the matter equation come out of it? It didn't seem right. Okay, and this is why. Do you understand? Okay, great. So now let's go back to our let's go back to more concrete things. We've got this equation, and we're going to study. I'm clearing, let's say. Okay. So last thing about the structure of the equations. Now, how many variables do we have in cosmology? Two variables. The two variables are epsilon and A. The two variables are epsilon and A. Okay? So we need two equations. We will also, of course, have to put in an equation of state. Two variables, two equations plus an equation of state should give us all our dynamics. Okay? So I'm going to derive one of these. You're going to derive the next one. I've got the easy one. We can go fast. Okay. So the equation I've set myself the goal of deriving is the equation of state. Okay. Now, oh, by the way, one last thing before we get there. It is sometimes useful, as we discussed, it is sometimes useful to work with a conformal time. So minus a squared of eta, the eta squared plus gamma ij dx I dx j minus. And when we actually solve the equations of cosmology, it will be easier to solve this here for some physical interpretations. Both these are useful coordinates. It's the same A, mind you, because A is the factor behind gamma ij. That is physical. Okay? Fine. So let's, for my purposes, I'll use this coordinate system, but we could have used either. Okay, so let's use this coordinate system and try to set up the equation of conservation of the stress tensor. Okay. So, very good. So let's go. So the stress tensor takes this form. Okay. So the stress tensor takes this form, and I've already processed it for you partly. So del mu t mu nu, I will only be interested in this equation. Okay. I will only be interested in this equation, and let me write it again as equal to minus u dot del of p minus u dot del of p plus minus u dot del of p plus how did it go? Del mu of epsilon plus p u mu is equal to 0. Actually, maybe this came, logically this came with a minus and this came with a plus. Okay, right. So this is my equation. Everything here is a covariant derivative. Not that. Okay, now life is very easy here because either we've got covariant derivatives of a scalar, which are ordinary derivatives, or we've got covariant derivatives of a vector, which is, now we are experts at that formula, right? Okay, that's the divergence of a vector. That's very easy. Okay, this is the only, you see, I should really be looking at all the equations of hydrodynamics, but this is the only one that will contribute. Why? Because you see, either we've got a free index T, which I focused on by dotting with U, or we've got a free index I, which by symmetry must give us 0. So the only content is in this equation, which is secretly the entropy conservation equation. Okay, so it's a very easy equation. Now instead of going through entropy and so on, I'll just process it like this. So what is this? Now, what was our metric? Our metric here was, so let me write down, what is U? In our situation, okay, in our situation, let me write down what U mu is. So U mu is equal to, you know, minus 1, or maybe plus 1, plus minus 1, 0, 0, 0. So that U mu upper will be plus 1 in the time direction. Okay? And so our and so U dot del was simply del T. So this part is del tau of P. Is this clear? U lower. I want U upper to be plus 1. U should be del x mu by del tau. Okay, it's how things move in. Yeah. Okay. So good. So this quantity here was just del tau P. What about this quantity? So this quantity is plus del mu 1 by square root g del mu square root g epsilon plus P U mu. Okay. Now what is square root g? Firstly, the only derivative that will ever that will count is the time derivative.
Yes.
Okay. So only the time derivative counts. Anything here that's not a function of time we can pull out. So square root g has a factor of square root gamma, but that's independent of time. That will cancel between numerator and denominator because you can pull it out. Okay. So the only thing that counts is this factor of a tau.
A to the 6
Square root.
yes,
Exactly. So this is del tau P plus 1 by a cube del mu a cube del T a cube of 1. And I have missed a minus sign because there was a minus sign in this. There's a minus here.
and the E plus P3.
And the plus. Okay. So this quantity here we can call 3 del tau log A, or I think Landau-Lifshitz likes to call it del tau log V. Let A cube be called V. It's the volume of the unit sphere divided by the volume of, I mean, it's the volume of the sphere of size A divided by the volume of the unit sphere. Okay. But let's, right, which is equal to del tau of log A cube. All these are equivalent things.
Epsilon and P are
Everything has an epsilon plus P.
P there, derivative is operating on epsilon and P times.
Oh, you're absolutely right. Thank you. 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 Epsilon plus P. Okay. Now let me yeah, I'll just open this up. Thank you for the correction. So we have del tau of P minus 1 by a cube del tau a cube into epsilon plus P minus del tau of epsilon plus P. All this, at least from here on. Now, the P here cancels the P here, and this makes it minus del tau E. So we have minus del tau E minus del tau log V, V is the say cube, times epsilon plus P is equal to 0. Okay, and therefore we have del tau E divided by epsilon plus P is equal to minus del tau log V. Or if you want log a cube, V may be unnecessarily confusing. Okay, so this you should think of as the first equation. Both sides here have a del tau, but that's a bit of a fake because both sides have a del tau. So you can think of this as an equation that is dE by epsilon plus P is equal to minus d of log a cube. And the logical structure of this equation is the following. Suppose I know P is a function of E. I plug that in and then I integrate this. That has given me now E in terms of a cube. So I've got rid of one of the variables, G, and then said there's no reason to suppose there's a cosmological constant at all. However, there is apparently. It's a mystery. Anyway, that we will get to that discussion. Okay? So, but anyway, there is a universe. Now, in this universe, what would happen? A would just be constant. Okay? So, what would the universe be? It would be d tau squared times a squared, constant squared times s3 squared if k was, in this case, k has to be minus 1 because if k is 0 or 1, this thing never skims. This universe is called Einstein's static universe. Einstein's static universe, and it's in fact the universe that we found when we were doing conformal compactification of Minkowski space. Do you remember our conformal thing was up to the conformal factor we found dt squared plus s3 squared minus dt3 squared plus s3 squared. At that time I told you that we'll encounter this universe when we're doing cosmology, and this is where we encountered it. Is this clear? Okay, so in this case there are three qualitatively different possibilities. Either this top is below, in which case it's the cosmological constant doesn't do much qualitatively. It skims the top, which it allows this solution, which Einstein didn't realize, but is in some serious physical way unstable. Okay, or you could be at the top and then you just go whoosh. You can be over the top and then you go whoosh. Okay, the last case we will study is the negative cosmological constant. So suppose the cosmological constant was negative. So this guy was a positive number. Okay, in that case, our potential will look something like this. This is the first time we need the positive axis for the potential. It would start doing something like this, and at some point, switch over, and at late times goes like that. It's something like this. So not a very. This wouldn't have got me into TIFR, I think. but something like this, right? Okay. And now you see that in this case, k equals -1, 0, and +1 are all basically the same qualitatively. All of them would have universes that do ship. Of course, details differ. Formulae will differ. But basically, this is what we have. Okay, great. I think that we will, apart from questions or comments here, we're stopping today's class. In the next class, what we will do is explore a little more the physics of being in such a universe. Okay, we'll explore redshifts and fun stuff. I'll talk a little bit about de Sitter space, and then maybe we'll move on to studying gravitational radiation. Look, by the way, this elementary basic discussion of cosmology. Of course, nowadays cosmology is a precision science. All kinds of things. But the elementary framework of cosmology is so simple. Just look at it. It's all a potential, a classical mechanics problem, something an undergraduate could study, but it needed general relativity. It's such a simple and beautiful application of the general theory of relativity, and once you've seen it, it's hard to forget. I mean, so simple. It's governed by two equations. One equation is what the matter is doing. Okay, that equation, maybe in this form is not so easy to remember, but in the form energy density times AQ for dust, and energy density times a to the 4 for photons, and energy density for the cosmological constant. These remaining constant is trivial to remember because it's got physical interpretation. All you need to do is put that into this equation. This equation, this term, by the way, as I'll tell you next time, has a name. It's called the Hubble constant. A dot by A. And this equation you sometimes in colloquia say as they put everything to the right hand side. So people talk about it as an equation for the Hubble constant. Hubble constant has, you would say, energy budgets. Hubble constant is equal to something plus something plus something, and one part is dust, one part is cosmological constant, one part is curvature, one part. It's just very simple stuff. You see, it's just very simple. The best way to think of it is a motion of a particle in a potential. And then after that, you can solve the problem. All the rest is detail. It's sometimes you can integrate the equation, sometimes you need Mathematica. Who cares? Basically, you understand the problem. Okay, we'll have a little more discussion on Friday, and we'll have a few exercises. But for now, let's.